In this video, we will explain how to compute bases for the null of A, column of A, and row of A. Remember that the null of A is the solution of a homogeneous system. In this case, the null of A would be the solution of this homogeneous system, x1 minus 2x2 and we know that this is a subspace of R4. The column of A, on the other hand, column of A is the span of the columns. That means it's the span of these vectors. And clearly, this is a subspace in R3. And finally, row of A is the span of the rows. And this is a subspace in R4. Then we can solve all the three problems of finding the bases just by doing row reduction. We can do row reduction for this, and then we end up that this matrix is row equivalent to this matrix. Then, to solve this problem, we just need to know that this system is equivalent to this system x1 minus x3 minus 2x4 equals 0, x2 minus 2x3 minus 3x4 equals 0. And since this system is a good system, we can decide what are the basic variables. Basic variables are x1 and x2, and the free variables are x3 and x4. Notice that the basic variables are those that goes with the pivots, with the pivot columns, and the free are those who doesn't have a pivot. Then we just solve the basic in terms of the free, and then we get that x1 is x3 plus 2x4, and x2 is 2x3 plus 3x4. And then we need to write the solution as a subset in R4. That means we write the solution as the vectors. Instead of x1, I write x3 plus 2x4. And instead of x2, I write 2x3 plus 3x4. And here x3 is free and x4 is free. Then we write it like this, such that x3 and x4 are, let's suppose that we are working with the real numbers, then are real numbers. And we know that essentially this is the span when we collect x3. Remember, this vector can be written as x3 times 1, 2, 1, 0 plus x4 times 2, 3, 0, 1. That means that this W, this space, which is the null of A, which is a subspace, is the span of these two vectors. The vectors 1, 2, 1, 0, and the vector 2, 3, 0, 1. And it is very clear that these two vectors are linearly independent. When you set up the system to prove that these two are linearly independent, the two last equations easily give us that the two weights must be 0 if you are trying to make a linear combination that produces the 0 vector. then these are linear independence. There will always be linear independence when you do this procedure. And that means that a basis for the null of A is given by these two vectors, right? Then a basis is 1, 2, 1, 0, and 2, 3, 0, 1. And it also means that the dimension of the null of A, which is called the nullity of A, is equal to 2, because we have that a basis has two vectors. Then the dimension of a vector space is the number of elements in the basis. Then we have that the nullity is 2. That means that the process of finding the null of A, we already know it. Essentially, we solve the system, and the dimension is going to be the number of free variables, and the basis is going to be given by those vectors that were called generator vectors. Let's compute a basis for the column of A. And let me just give you the answer, and then I will explain why. To compute a basis for the column of A, the only thing that we need to do is we need to select those columns from the original matrix that goes with the columns that has a pivot. Here we have that first column has a pivot, second column has a pivot, and therefore in this case we have that a basis for column of A, which is denoted by C of A, is the set given by these two vectors, 1, 4, negative 13, and negative 2, negative 5, 11. Essentially, we pick these two because these two columns, they go with columns that has pivot, and we disregard these two. But let me explain why we disregard this vector, for example. If we try to answer the question, are these three vectors linearly independent? Then we will have to set up this system of equations. Just forget about the part that has x4 here. Right? We set up this system of equations, and we try to see if we can find a free variable. If we can try a free variable, then we will get that the vectors are linearly dependent. And then when we do row reduction, we will end up with this matrix. This equals 0, this equals 0, and this equals 0. That means that x3 will be the free variable, and that means that we can write, essentially we can write the third vector as a linear combination of the other two. Same way, since here this column doesn't have a pivot, that means that this vector can be written as a linear combination of these two. When we try to set up the equation of making this vector a linear combination of the other two, we get to a system that can be solved explicitly. And since this can be written as a linear combination of these two, and this can be written as a linear combination of these two, then they are not needed. And therefore, a basis for the column of A are just these two vectors. Then, in general, to compute the basis for the column of A, we do row reduction. We see what columns has a pivot, and then we select those columns that goes with those columns that has a pivot, and we disregard the other columns. Then, in this case, the dimension of the column of A is also 2. By the way, the dimension of the column of A is called the rank of the matrix A. The dimension of the column of A is the rank of the matrix A, and the dimension of the null of A is called the nullity. And there is a very important theorem that says that the nullity of a matrix plus the rank of a matrix is the number of columns. That theorem is very easy to prove because essentially when you solve the system, we notice that we get these two vectors that are bases. There are as many of these vectors as free variables. That means that the nullity of A when you do row reduction is the number of free variables. On the other hand, a basis for the column of A, we need to pick those vectors that goes with the pivots. That means that the dimension of the column of A, which is called the rank of A, is the number of columns with a pivot. The nullity is the number of columns that don't have a pivot. And therefore, we have that the rank of a matrix plus the nullity of a matrix is equal to the number of columns. Finally, for the root of A, here we have three vectors, and we want to find a basis. We are going to do something slightly different. We can see that anytime we do row reduction, the set of new rows that we get, they expand the same set as the original rows. Then when we do row reduction, each row is a linear combination of the previous rows. And therefore, when you do linear combinations of the rows, and let me try to explain it better. If we have A and we get the matrix B by doing row reduction, then the span of root of A is equal to the span of root of B, because at any step, each new row in B is just a linear combination of rows of A. And remember that we can't, row reduction, row operations are reversible. Then you get the same argument saying that every root of A is a linear combination of those rows in B. For that reason, a basis for root of A is just the rows that are non-zero when you get to an echelon form. It doesn't have to be reduced echelon form. Then a basis for root of A is just these two rows. 1, 0, -1, -2, and 0, 1, -2, -3. Notice that the dimension of root of A is equal to 2, which is always the same as the dimension of column of A. And the reason is because these two numbers are just the number of columns with a pivot after doing row reduction, or after getting the echelon form. You get the echelon form, you count the number of pivots, that's the dimension of column of A, that's the dimension of row of A, and this is also called the rank of A. Notice that this technique that we have seen helps us to compute the basis of any span of any vectors. Let's suppose that we are asked, find a basis for the span of these vectors. Let's suppose that you have the span of these vectors 1, 1, -1, 2, 3, 1, 1, 4, and 2, 1, 0, 1, and let's just say these three vectors. How do we find a basis for this vector space? We know that the span of any vectors, any collection of vectors, is a vector space, and if we are asked to compute a basis for this subspace, essentially we create the matrix A equal to 1, 1, -1, 2, 3, 1, 1, 4, 2, 1, 0, 1, and then we just compute a basis for column of A, because column of A are these three vectors. In this case, remember, essentially we do row reduction, and we say this is row equivalent to the matrix 1, 0, 0, 0, 1, 0, 0, 0, 1, 0, 0, 0. That means that in this case, each column of the reduced echelon form of this matrix has a pivot. That means that a basis for column of A is just the set. You need the three columns, and it's 1, 1, negative 1, 2, 3, 1, 1, 4, and 2, 1, 0, 1. And yeah, this is a basis, and that means that the rank of this matrix, rank of A, which is the dimension of column of A, is equal to 3. Notice that this is an easy question. What is the nullity of A? Nullity of A, which is the dimension of the null of A. Remember that we have that the nullity plus the rank must be the number of columns, but there are 3 columns and the rank is 3. That means that the dimension of the nullity is 0, and that means that the null of A in this case is just the vector 0, 0, 0. An interesting observation is that the rank of a matrix is the same of the rank of the transpose of a matrix. Let me remind you that the transpose of a matrix is the matrix that we get when we change the columns with the rows. Then here I get matrix 1, 1, negative 1, 2, 3, 1, 1, 4, 2, 1, 0, 1. And the reason is because the rank of A transpose is just the dimension of the column of A, right? But in this case, the columns of this matrix are the rows of this matrix. And we already pointed out that the dimension of row of A is just the same as the dimension of column of A. The dimension of row of A is just the dimension of column of A. And remember that this is just the number of pivots when you do row reduction. And therefore, here, when you think about the rank of A transpose, this is the dimension of the space column of A transpose, but column of A transpose, this is just the dimension of row of A, because the columns of A transpose are the rows of A. And this dimension is just 3. Actually, from the previous argument, we know that a basis for row of A to compute a basis for row of A, we just do row reduction and we pick the rows that has a pivot. Then in this case, it is just 1, 0, 0, 0, 1, 0, and 0, 0, 1. Then again, when we are given a set of vectors and we want to compute a basis, we just can generate a matrix with those vectors as columns, and we can do the previous argument. Actually, we could also generate a matrix whose those vectors are the rows, and you can do the argument of computing row of A or column of A.